In this video, we're going to look at a specific example of how differential calculus can be used to determine maximum and minimum values of given functions. So displayed on the screen here, we have the function s, which is a displacement, equals 1.5 e to the power of minus 4t sine 12t. Now the way that we're going to evaluate this is to first of all find the first derivative of the function, and the first derivative of the function is the gradient. Now where the gradient of the function equals 0, we have either a local maximum or local minimum for that function. We'll then need to find the second derivative, because the second derivative can be used to tell us whether it is in fact a maximum or a minimum that we have when the gradient equals 0. Now in this particular example, it's first of all useful to take a look at the function on a graph, just to give us an idea of exactly what it is that we're trying to determine. So displayed on the screen here, we have the function s equals 1.5 e to the power of minus 4t sine 12t. So it's exactly the same function as we had previously on the screen. Now the way that I've generated this graph for the function is by first of all listing a range of values of t, increasing in 0.005 second increments, and then I've inputted the formula for our function as equals, open brackets, 1.5 times the exponential of minus 4 times a2. The reason it's a2 is because it's cell referencing our time here, times sine of 12 times a2. Note that by default Excel works in radians, and when we have a sinusoidal function involving time, we generally work in radians. So we don't need to carry out any conversions here. Next, I highlighted our time column and our column for the values of s, and I just produced an xy scatter. So what we have on our x-axis is time, and on our y-axis we have the value of s, or the displacement. The simplest way to think of this is if we have a mass oscillating on a spring, the mass is going to go up and down with respect to time, and as energy is lost, the magnitude of those oscillations is going to decrease. Now you'll notice that there's a third column here, and the third column is just for the first part of that function, 1.5 e to the power of minus 4t. So again, I've inputted a formula, equals 1.5 times the exponential of minus 4 times the column for t. And I just want to show you how that appears when added to our graph. So here we can see that the exponential function has been added to the graph, and what we actually end up with is something called an envelope on the graph. So here we have a sine function which is enclosed within our exponential function. These two lines would meet again at a later time. So it's useful to understand what we actually have is we have our sine function, and our sine function sits inside the exponential function or the envelope function. When it comes to determine maximum and minimum values, we need to determine the value of s at this point here, which is the maximum value of the function of s, and we can see that it's just below 1. And then we're going to determine the minimum value of s, which occurs around here, and we can see that that's probably somewhere between minus 0.3 and minus 0.4. So we know what we're aiming for, and what we can do is prove that using first and second order differentials. So let's return to the problem on the previous screen. Okay, so the first stage in this problem is to find our first order derivative, or ds by dt. Note that as s is a displacement, ds by dt is the velocity. Now what we have here is a product of two functions, so we're going to need to use the product rule. And the product rule states that ds by dt equals u dv dt plus v du dt. So u dv dt plus v du dt. Now before we can solve this problem, we need to assign our values of u and v. Now what we're going to do is we're going to set 1.5 e to the power of minus 4t as u, and we're going to set sine 12t as v. So therefore we have u equals 1.5 e to the power of minus 4t. And we have v equals sine 12t. But we know that we also need the derivatives of each of those with respect to t, because here in our formula we have dv by dt, and here in our formula we have du by dt. Therefore, du by dt, differentiating with respect to time, we get minus 6 e to the minus 4t. And differentiating v with respect to time, we have dv by dt equals 12 cos 12t. Note that sine differentiates to cos. Okay, so now we can bring that together because we have ds by dt equals u dv dt. So we're combining our u and our dv by dt. Note that the coefficient at the front of u is 1.5 and the coefficient at the front of dv by dt is 12. So in order to cut down on the number of steps, I'm going to combine those two coefficients. 1.5 times 12 is 18. So we have 18e to the minus 4t cos 12t. Now what I've written there represents u dv dt. And next, I can include v du dt. Note that at the front of du dt, we have a negative number, minus 6. So although the original form is plus v du dt, I need to take account of that minus 6. So I'm going to get minus 6e to the power of minus 4t, and then sine 12t. In actual fact, what I've written there is du dt times v, but I want to keep these two terms in the same format. Now recall that we have turning points or maximum minimum values of this function when our first order derivative equals 0. Now if we think of that in the context of a mass oscillating up and down on a spring, like so, then what we're basically saying is when the first order derivative equals 0, the velocity of that mass equals 0. And that makes sense because at the top and bottom of the movement, the mass stops before it starts moving in the opposite direction. So we have positive velocity, the mass stops, and then we have negative velocity as it drops back down. So we need to set our first order derivative to 0. Now what we have there is going to be quite complicated to rearrange and set to 0, so we need to have an intermediate step. And what we need to do is look at simplifying one of these two terms. We have a cos term and we have a sine term. Now the way that we're going to do this is by dividing each of those terms by the term on the left hand side here. So we're going to divide each term by 18 e to the minus 4t cos of 12t. So what's that going to leave us with? Well, if we divide anything by itself, here we have 18e to the minus 4t cos 12t divided by 18e to the minus 4t cos 12t. It doesn't really make any difference what we divide by itself. Anything divided by itself always equals 1. It could be 4x squared divided by 4x squared. It could be 18e to the minus 4t over 18e to the minus 4t. It could be cos 12t over cos 12t. It doesn't actually make any difference. But dividing something by itself leaves us with 1. Now what are we going to get for our other term? Well, let's write this out longhand first of all. We have minus 6e to the minus 4t sine 12t. divided by 18e to the minus 4t cos 12t. Now, for the reasons just mentioned, we can simplify this because anything divided by itself just equals 1. E to the minus 4t divided by e to the minus 4t is just 1, so we can actually cancel those out. And hopefully you also recall that sine theta over cos theta equals tan theta. So in actual fact, what we can do here is simplify our function further. We can say that ds by dt equals 1 minus 6 over 18 as a fraction. Well, 6 over 18 is the same as 1 over 3. And sine 12t over cos 12t is just tan 12t. So all I've done there is separate out our terms. 6 over 18 has become 1 over 3, and sine 12t over cos 12t has become tan 12t. Okay, I'm going to move that first order derivative to the top of the page, and then I'm going to clear some space. Okay, so now we have our first order derivative in the top right hand corner. We can set that equal to 0 to find where our turning points are. So we have 1 minus a third tan 12t equals 0. So we're setting the velocity equal to 0 to see where our turning points are. Let's add a third tan 12t to each side. So we get 1 equals a third tan 12t. And then let's multiply each side by 3. So we end up with 3 equals tan 12t. Recall that we're trying to find t, so I'm going to take tan to the minus 1 of each side. I'm going to get 12t equals tan to the minus 1 of 3, and my last step will be to divide each side by 12. Therefore, the value of t, where we have our first turning point, is 0.1041. That will be in seconds, and that's accurate to 4 decimal places. You have to make sure that your calculator's in radians here for the reasons mentioned earlier. So now we know the time where the first turning point occurs. So what we can determine is the displacement at that turning point, or the maximum displacement of that function. And the way that we do that is just by inputting our value of t. So we have the displacement s, and I'm just going to put a subscript 0.1041 equals, and all I do here is input the 0.1041 as t here and as t here. Now, to improve accuracy, I'm actually going to keep my full calculator answer, which is actually 0.104087 and so on. And I'm going to input the formula replacing t with the answer, or ANS on my calculator. So I'm going to input the following: 1.5 e to the power of minus 4 times answer times sine, open brackets, 12 times the answer, close brackets, equals. And the answer I get for that is 0.938, accurate to 3 decimal places. So 0.938, and let's specify our displacements in millimeters. All that means is our original function was for displacement in millimeters. The units are somewhat arbitrary here. Okay, let's check what we've got there on our graph, and then we can go on to determine the position of our minimum. Okay, so referring to our graph, we've just stated that our maximum occurs at a time of 0.1041 seconds, so somewhere around here. And we've calculated the value of the displacement at that point to be 0.938. So with reference to our graph, we can see that those answers are likely to be accurate. Next, we need to determine the location of our second turning point here. And then we can determine the displacement at that point also. Okay, so in order to determine the location of our second point, we need to recall some theory from when we looked at graph sketching. Because we know the function sine t, as an example, will repeat every 2 pi radians. Therefore, the peak-to-peak distance would be half of that, or pi radians. But we don't have the function sine t here. We have a product of the function sine 12t. Therefore, the function sine 12t repeats one full cycle of 2 pi over 12. Sine 12t completes 12 full cycles in the time sine t completes one cycle. So because the time taken for sine t to go from peak to peak is pi, therefore the time taken for sine 12t to go from peak to peak is pi over 12. Now, pi over 12, if you run that through your calculator, has a value of 0.2618. So what we have here is we have our distance to the first peak, or the first turning point on our graph, of 0.1041. And the distance to our next peak is going to be an additional pi over 12, or 0.2618. Therefore, to find the time to our second peak, we just need to add pi over 12 onto our original value of 0.1041. Now, if we add those two values together, we get an answer of 0.3659, which appears to correlate with what we have on our graph here. So the value of t at our second turning point is 0.3659. Let's return to our calculations. So we know that our second turning point occurs when t equals 0.3659. And if you're unsure, you can actually just input that value of t into the first order derivative. And in doing so, you'll get an answer of 0. Because at that value of t, the first order derivative, or the velocity, must equal 0. We have a change in direction. So you may want to try that for yourself. But I'm going to go on and calculate the displacement at that point. And the displacement at that point is the displacement when t equals 0.3659. And again, all I'm going to do is input that value of t into the original function. And that gives me a value of s equal to minus 0.3293 millimeters. So therefore, we know the maximum and minimum displacements of that mass as it oscillates on the spring. Now, you may be asked to check that using the second order derivative. We know from our graph that the value of 0.938 is in fact a maximum, and we know that the value of minus 0.3293 millimeters is in fact a minimum. But we can actually prove that using the second order derivative. And I'm going to demonstrate how in this next stage of the video. I'm just going to take a step back, and what I'm going to do is return to our first order derivative, so ds by dt, but before we did the simplification, that gave us 1 minus a third tan 12t. And we'll pick up from that point in order to find our second order derivative. Okay, in order to find our second derivative, d squared s by dt squared, or the acceleration, we're going to need to apply the product rule, but we're actually going to need to apply the product rule twice. We're going to need to apply the product rule to evaluate this term here, and we're going to have to apply the product rule to evaluate this term here. So we're going to have two values of u and v. So let's call them u1, v1, u2, v2 for reference. And I'm going to add my values of u1, v1 and u2, v2 in the top right hand corner. So I have u1 equals 18e to the minus 4t. Therefore, the derivative du1 by dt is minus 72 e to the minus 4t. I have v1 is cos 12t. Cos differentiates to minus sine, so dv1 by dt is minus 12 sine 12t. Let's repeat for u2. So we have u2 equals minus 6e to the minus 4t. Therefore, du2 by dt, the derivative of that, minus 6 times minus 4 is 24, positive. 24e to the minus 4t. v2 is sine 12t. Therefore, dv2 by dt, the derivative of that, is just 12 cos 12t. So again, it looks like we're going to end up with something quite complex, but in actual fact, it simplifies down quite nicely. So we have u dv dt for the first term, so u1 and dv1 by dt. We can multiply out the coefficients like we did before. We've got 18 and minus 12. 18 times minus 12 is minus 216. So we have minus 216 e to the minus 4t sine 12t. And to that we need to add v du dt. So v1 and du1 by dt, which is minus 72 e to the minus 4t cos 12t. Now we need to repeat that for u2 and v2. So we need to add on u2 dv2 by dt. These two here multiplied together. Now minus 6 and 12 is minus 72. So we have minus 72 e to the minus 4t cos 12t. And finally we have v du dt, again using v2 and u2, which is 24 e to the minus 4t sine 12t. Okay, now because we have two terms involving sine and two terms involving cos, we can actually combine these. So we have minus 216 e to the minus 4t sine 12t. And to that we need to add 24e to the minus 4t sine 12t. All we need to do is add the two coefficients. So minus 216 plus 24, which equals minus 192. And the rest of that expression remains the same, e to the minus 4t sine 12t. And we can do exactly the same with our two cos terms, because we have minus 72e minus another 72e, which is minus 144e to the minus 4t cos 12t. So we've managed to simplify our function. We have one last step to prove that what we actually have is a maximum when t equals 0.1041, and to prove that we have a minimum when t equals 0.3659. And the way that we do that is by inputting each of those values of t into our second order derivative. Recall that if we have a maximum, the second order derivative must be negative. And if we have a minimum, the second order derivative must be positive. Now what d squared s by dt squared represents is actually the acceleration. So where we have a maximum displacement, we have a downwards acceleration. And when we have a minimum displacement, we have an upwards acceleration. So the mass is constantly being accelerated towards the centre line. Okay, we have d squared s by dt squared when t equals 0.1041. And when we input that value of t into the function above, so inputting the value of t here, 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 and here, we get a value of the function equal to minus 150.131. Which is clearly negative, so we've proved that we have a maximum when t equals 0.1041. Let's repeat for our second turning point. So we have d squared s by dt squared with a value of t of 0.3659, and inputting 0.3659 into the function above, we get an answer of 52.684, which again is positive, meaning that we have a minimum when t equals 0.3659. So just to summarise, we use the first order derivative in order to determine the time where our turning points occur for this function. Once we had the time where the turning points occurred, we was able to determine the displacement at each of those turning points. Once we had the displacement at each of those turning points, we then found the second order derivative, noting that if the second order derivative is negative, then we have a local maximum. And if the second order derivative is positive, we have a local minimum. We've also observed the function on the graph in order to validate each of our calculations.